In this video, I want to do a slightly more complicated example of combining capacitors and calculating equivalent capacitance. And specifically, I want to think about this circuit here where I have a couple of capacitors that are in parallel, and those capacitors in parallel are in series with another capacitor, and they're connected together with some power supply or battery that has a potential across it of 10 volts. We'll say that each of these capacitors, to make the problem numerical, we'll call them, say they all have 5 microfarads worth of capacitance. And the question here is has a couple different parts. First, I want us to find the equivalent capacitance of this whole system. That is, if I took out all 3 of these capacitors and just wanted to replace them with a single capacitor, what would be the capacitance of that capacitor? But then I also want to know, what are the charges on all of the different capacitors? How much charge is on each capacitor? And how much potential do you have across each of these capacitors? And it's not always the most straightforward to do that, and so I want to show you that the key to solving these problems is sort of staying super organized, all right? So let's dive in and see how we do this, how we find the equivalent capacitance, all the Q's and all the V's. So, well, first of all, when we have more complicated circuits, we want to draw sort of some equivalent, easier to work with circuits, right? So one thing I could do is I could take these 2 capacitors that are connected in parallel. I know they're in parallel because there's a split here in the wire. So I could take those, and I know I could combine those, sort of think, well, what if I replace that with one equivalent capacitor? And if I did that, then I would end up with a circuit that looks sort of like this. It would have a power supply in it, and then it would have a capacitor C1, and then we'd move along, and now we'd have a new capacitor, and I would call this is capacitor 2, 3, right? Because it's sort of the combined or equivalent capacitance of 2 and 3, right? So I'll call that capacitor 2, 3 there. This would be an equivalent circuit. And then, if I wanted to think about, okay, the total equivalent circuit, now I have 2 of them in series, I could combine those together, and I would end up with a circuit that would just look like this, that has a power supply with potential across it V, and just one capacitor, and that capacitor, is the combination of all 3, so I could call that C1, 2, 3, right? And this is V, right? The V across is going to just be whatever the V is across this capacitor, right? So I could also just write that as V1, 2, 3, right? It's the total V across this equivalent capacitor. So these are sort of my equivalent circuits here that I want to deal with. And so sort of a good first step is you want to figure out what this C23 is and what C123 is. We want to reduce the circuit. And to sort of keep organized, I find it really helpful to make myself a little table where I'm going to, in the table, I want to keep track of the capacitance, and I want to keep track of, and that's going to be in units of microfarads, right? I want to keep track of the amount of charge. If this is in volts, charge is going to end up coming out in microcoulombs. And I want to keep track of the potentials across each capacitor, right? And potentials here in volts. You might recall that these 3 things are all connected, these 3 quantities are all connected by one formula, right? That is that capacitance is Q over V, right? So that will be a useful formula later. We'll want to use that at several points. So these are the 3 things I want to keep track of, and so but then I need to think about what are all of the different things in my circuit. Well, I have capacitor 1, capacitor 2, capacitor 3, and then I'll also want to keep track of this capacitor 2, 3 in my combined circuit, and the total capacitor 1, 2, 3, right? The total combination there. So let me just sort of make this a clear table. All right, and so the goal here in this problem is sort of to fill in all of the quantities in this table. And so we can do that just by putting in our givens. So we were given that all three capacitors have 5 microfarads, and we were given that the potential across the whole thing is 10 volts, right? So these are our givens. Maybe I'll put a little box around them just to note that this is a given, this is a given, and this is a given. All right, so now we know our givens. Okay, so what do we do from here? Well, it would probably be helpful to sort of work our way down this table and find out what these equivalent capacitances are. So first, let's see if we can figure out what capacitor 2, 3 is, what the combination of capacitor 2 and capacitor 3 is. And we see these are in parallel, so we remember our capacitors in parallel formula. We look it up, and that we get that C23 is just going to be C1 plus, or sorry, C2 plus C3, right? Just the combination of the two. And so that's just going to give us 10 microfarads, right? Adding those two together. So I'll put a 10 here. So now that's good. We've got C23, so now we can get C123, right? And we remember our formula here. These two, C23 and C1, are in series with each other. So we know that 1 over C123, 1 over the equivalent capacitance, is equal to 1 over C1 plus 1 over C23, right? Because these two would be in parallel or in series, and this is the series formula. And so if you go and you plug in 1 over 5 plus 1 over 10, you end up getting 3.3 microfarads from that. All right. So, and then inverting, right? 1 over 3 plus 1 over 10, and then inverting, you get that C 1, 2, 3 is 3.3 microfarads. So I'll go ahead and write that in the table. So I guess technically 1 over 3.3. There we go. And so great, we filled in sort of a whole column here. We now know what the equivalent capacitance of this system is 3.3. But we're not finished, because we are also asked to find out, well, how much charge is on each of these capacitors and what's the potential across each of them? Well, now we maybe can start to see the benefit of putting things in a table here, because we can notice, well, I know the equivalent capacitance of the system, and I know the potential across the whole system, right? The potential across the whole system is 10, and I know that C is Q over V, so I could rearrange this and get that Q is going to be C times V, right? So I could get Q1, 2, 3, right? Q on this capacitor right here, right? The Q in sort of the whole system is going to be 10 times 3.3. That's going to be 33 microcoulombs, right? Okay, that's good, but now how do we actually break into this section here, right? So if I know any two, I can get the third, so that's nice, but how do I break into this section here? Well, we need to think about sort of working our way back up into this circuit, right? So on this circuit, now we know what the Q's are, we know what the C's are, we know what the V's are. And this is a series circuit, right? This equivalent circuit was a series circuit. And so it's helpful to think, what is the same in a series circuit? What's the same in a series circuit? And well, if we remember, in series circuits, the quantity that's the same is Q, right? It's the amount of Q that flows out, hits this one, is also going to be the amount of Q on this one. So we can note that Q1, 2, 3 here is going to be equal to Q on 2, 3, and is also going to be equal to the Q on 1, right? Because those are all in series, right? Whatever the Q is that hits 2, 3 is also going to be the Q that hits number 1. So all of these have the same Q, so we can go ahead and fill those in. That Q on 2, 3 has 33 microcoulombs, and that's also going to be the amount of Q on 1, 33 microcoulombs. Well, now you can notice that we've already got, now we have C and Q, so we can figure out what the potential difference is across these, right? And and you're going to notice it's a different amount of potential difference. So let's see if we can calculate it here. So to get the potential difference V is going to be Q divided by C right? So I need to take Q and divide by C. So I do 33 divided by 10 here, and I get a potential difference of 3.3 volts across this equivalent capacitor 2,3. And here I'm going to do 33 divided by 5, and that gives me a potential across that one of 6.7 volts. And hopefully this makes some good sense that across 2,3 here, I had a drop of 3.3, and to get all the way down a hill that's 10 high, I would need to go 6.7 more, right? So if I went 3.3 across this one and 6.7 across this one, I end up back down at 0, and then I'd go back up 10, right? And then down 3.3, down 6.7. So it makes sense that if I have that these two add together, right? Because the potentials need to add together for a series circuit. All right, but we're not quite finished because now we need to figure out something about C2 and C3, right? So how are we going to work out information about C2 and C3? Well, now it's again useful to think about what is the same, right? What's the same between C2, C2, and C3? What do these, what is something in our circuit that we're looking at, our equivalent circuit, what do they have in common with these two capacitors? And well, the thing that this has in common when you're talking about things in parallel, the thing that is always the same is the potential, right? So in this case, we know that the potential across 2, 3 must be the same as the potential across 2, must be the same as the potential across 3, because when things are parallel, that means the potential is the same, right? So this is because they're parallel, right? Well, this was because they were in series. All right, so if the potential here is the same, then we can go ahead and fill in here that this potential is 3.3, and this potential must also be 3.3, right? And now that we know the potentials, we can go ahead, we know potentials and capacitance, we can go ahead and calculate Q, right? Q is C times V. And so I can do 3.3 times 5, and I get 16.7 microcoulombs, and that'll be the same for both of them, 16.7 microcoulombs. And so now, there you have it. We've calculated what the Q is on each of these different capacitors and what the potential is across all of the capacitors as well. All right, so it looks like the potential across each of these would be 3.3, and the potential across this guy is 6.7, and we have also the amount of charge on each of them. If you had different values for these capacitors, that would be fine. You'd work through it the same way. The key is to always look and see what's the same. What's the same between these two circuits? If it's a series circuit, the thing that's the same is charge. If it's a parallel circuit, the thing that's the same is the potential.